6, piecewise and step functions. So graphing piecewise defined functions. Some functions cannot be described by a single expression because they are defined differently depending on the interval of x. These functions are piecewise defined functions. A piecewise linear function has a graph that is composed of some number of linear pieces. So we have an example here where we're going to have linear piecewise pieces. So for this first one, it says to graph a piecewise defined function, graph each piece separately. So we're going to graph that first part of 2x plus 4, and then we'll graph the negative x plus 2. But I have my two tables here that we're going to go ahead and fill out for these. So the first table we're going to fill out, I have 1, 0, -1, -2, and -3 listed. So that is going to be when our x was less than or equal to 1. So this is the function where it's 2x plus 4. So we go ahead and we plug those in for x. So we're going to have 2 times 1 plus 4. 2 times 1 is 2. So 2 plus 4 is going to get us 6. So that point would be 1 comma 6. Then we can go ahead and plug in that 0. So we have 2 times 0, which is 0, plus that 4 gets me 4. So that point would be at 0, 4. Then we can plug in 1, or -1. So we have 2 times -1 plus 4. 2 times -1 is -2. Plus 4 leaves us with 2. So that's -1 comma 2. We have 2 times -2 plus 4. 2 times -2 is -4. -4 plus 4 gets us 0. So that point would be at -2, 0. Then we can plug in that -3. So I have -2 times, or I have 2 times -3, which is -6, plus 4, which is -2. So that point would be -3, -2. Okay. Now, if we look up in our inequality, this says equal to, so it has less than or equal to, which means the point that has the 1 is going to be a closed circle when we start drawing that part of the line. So when I go down to fill out the next piece of information, which is going to be when our x is more than 1, that's for the -x plus 3. So when we go to fill this out, we're not going to have that equal to piece, which means this first point where we start our line will be an open circle. So we're going to plug in 1. So we have -x, so -1 plus 3. That gets me 2. So that point would be at 1, 2. I would have a -2 plus 3. That would leave me with 1. So that point's 2, 1. I'd plug in 3. So I get -3 plus 3. That gets me 0. So that point is 3, 0. I'd plug in 4. So I have -4 plus 3, which is -1. So that's at 4, -1. And then I would go ahead and plug in that 5. So I'd have -5 plus 3, which is going to get me -2. So that point is at 5, -2. So now I'm going to scroll up to the top here where we're actually going to go ahead and graph those points. So when we go to graph this, I told you we'll start the one line at 1, 6, and it's going to be a closed circle because we know that our x is equal to in that part. So I go 1, 6, fill in a circle. Then I would just kind of plot my other points to help me finish getting this line. So we had 0, 4, we had -1, 2, we had -2, 0, and then we had -3, -2. So this line looks like this as it keeps going. Okay. Our other one since it was when we just had x's greater than 1, I told you it's going to be an open circle. So at 1, 2, we have to draw an open circle to start our line. And then we'd go ahead and plot the rest of the points. So I had 1, 2. Then we had the 2, 1. We had 3, 0. Then we had 4, negative 1. And then 5, negative 2. So this line would continue like that. So this is what our graph ends up looking like. Now I also wanted us to state the domain and range. So our domain is that our x values. So when I look at this, my graph, since it continuously goes left based off the arrow down here, and then it continuously goes right based off the arrow down here, that tells me my domain will be all real numbers. Because no matter what x I pick, there is a point that exists on this graph. Now for my range, it works a little bit differently. Because if I look, the highest point in my graph is up here at the 6, and then it only goes down. It never goes above 6, which means my range has to be when y is less than or equal to 6. So that is going to be our domain and range for this piecewise function. Now we're going to talk about a step function. So a step function is a type of piecewise linear function with a graph that is a series of horizontal line segments. So we're going to have a bunch of horizontal line segments in order to make a step function. One example of a step function is the greatest integer function, written as f of x equals, and it has a double bracket with x inside of it, in which f of x is the greatest integer less than or equal to x. So here, it kind of explains some of the key features and stuff. So the type of graph is that it's a disjoint line segments. The graph of a step function is a series of disconnected horizontal line segments. The domain is all real numbers because the dots and circles overlap, causing it to go through all x values, where the range is all integers because the function represents the greatest integer less than or equal to x. So it never goes through decimals or anything like that. Our y is always on those integers based on how it's written. So we're going to go ahead and practice that in this next example. So I have a table already created for us with us plugging in some x values, and we're going to see what we get out, but then we have to apply what that function means, so our greatest integer. So if I plug in negative 2, I take negative 2 plus 1, which is negative 1. Okay. Then I would take negative 1.75 plus 1, which is going to be negative 0.75. Negative 1.25 plus 1 is negative 0.25. And I'll just fill out all these x plus 1 values. So negative 1 plus 1 is 0. Negative 0.5 plus 1 is 0.5. Negative 0.25 plus 1 is 0.75. 0 plus 1 is 1. 0.25 plus 1 is 1.25. That one shouldn't be there. 0.5 plus 1 is going to be 1.5. If I take 1 plus 1, that gets me 2. 1.25 plus 1 is 2.25. 1.75 plus 2.25, or plus 1, is going to be 2.75. So all I did was I added 1 to each of these x values. Now is when we apply the greatest integer. So remember it said on that previous page that our greatest integer is going to be the greatest integer less than or equal to x. So when we look at this, when we plugged in -1, -0.75, and -0.25, all of them ended up getting us a number that was greater than -1, but it's less than the next integer, which is 0. So all 3 of these top numbers up here got us a number that is greater than or equal to -1, but less than 0. So that's what I wrote this, have this box for. So -1, -0.75, and -0.25 are greater than or equal to -1, but less than 0. So remember, for the function, we write the integer that they're greater than. So since they're all 3 greater than -1, all 3 of these then become -1 in our graph. For the next one, if I look at 0, 0.5, and 0.75, those are all greater than or equal to 0, but they're less than the next integer, which is 1. So that means all 3 of these would become 0 when I apply the greatest integer function. The next 3 are 1, 1.25, and 1.5 are greater than or equal to 1, but they're less than the next integer, which is 2. So all 3 of these would become 1 in this function. So in these last ones here, where we got 2, 2.25, and 2.75, those are all greater than or equal to 2. But they're less than the next integer, which is 3. So that means all 3 of these would become 2. So when we go to graph this, based off what we started with, so when we plugged in -2, we got out -1. So we would have that point filled like this. And then all of our values, until we got to -1, because -1 got us 0, stay at -1. So all of these values, until we get to -1, stay there, and then that circle would be open. Once we got to -1, we jumped up to that 0, but then it stays there until we got to our next value when we plugged in 0. 0 got us 1, and then it stayed there until we plugged in 1, which ended up getting us 2, and then that stayed there until the next one. And that's just how it repeats. So it's starting filled in, ends open as we go. And then you could even go the other way to finish out your graph, which would look like that, where we have the open going to the filled in. So that's what our function would end up looking like. Now, this last part here is just going to be a step function like this, kind of, but it actually gives us our range. So we don't have to apply something into the formula to get it, it tells us what it's going to go up by each time instead of us having to find the greatest integer. So this one's a word problem. So a state requires a ratio of 1 lifeguard to 60 swimmers in a swimming pool. That means that a lifeguard can watch up to and including 60 swimmers. Make a table and draw a graph that shows the number of lifeguards that must be on duty, f of x, based on the number of swimmers in the pool, x. So when there's 1 lifeguard, that means we have somewhere between 0 and 60 swimmers. Okay. Once we get above 60, we then have to add another lifeguard. So when it's between 60 and the next 60 people, which would be 120, we have to have 2 lifeguards. Once it goes above 120, we have to add in a 3rd lifeguard until we've reached 60 more people, so 180. Once we go over 180, we have to add in a 4th lifeguard until it hits that next 60 interval, which is going to be at 210. No, I'm at 240. Then when it's at 240, or above 240, we're going to add in our 5th lifeguard until it hits 300. Then when it's at 300, we get to stay at 6 lifeguards until it's over 360. Once it's over 360, we add in a 7th lifeguard until we're getting more than 420 people. So each of these ranges had to cover the 60 people, and each time we added in 1 lifeguard. So we're going to go ahead and graph these. So based off how it's written, when we have 0 lifeguards, 0 people, we would have that 1 lifeguard, and then it hits 60. Once it hits 60, we then have to start worrying about 2, but it's not until it's more than 60 to 120. So if you look, when I wrote each of these, I wrote it like this, meaning this part, it's when it's more than that number, we added in a lifeguard. So we have the open circles, where once it hits this, it's going to change right after that number. So that's why it's closed there. So it was 3 in this range, 4 here, 5, 6, 7. So then our graph ended up looking like this. So that is going to be it for our 4.6 piecewise and step functions.